Hi everybody, welcome to another video in Calculus 1, section 2.5, limits at infinity. So limit at infinity is concept is easy. X will go to infinity or go to negative infinity. I have a typo here. Sorry. Yeah, this is limit at negative infinity. So x go to infinity or x go to negative infinity. Clear enough. And in this case, the function, when x go to infinity or negative infinity, the function may have the limit from that side or that side. So simple enough. And furthermore, if when x go to infinity, the function go to a constant, y equal to that constant, is the horizontal asymptote. As opposed to previous section where we have infinite limit, we have the vertical asymptote. This one we have the horizontal asymptote. When that constant y equal to a constant, and that constant is the limit of the function when x approaching to positive or negative infinity. Right. So let's look at the graph of that one. So we just look at that graphically, and then later on we will do that numerically, or even better, algebraically. Right. I have x. I just put in fraction form. I have x divided by square root of x squared plus 1. Right? So that is the graph. Look like this. So the limit when x go to infinity look like it will go to 1. And when x go to negative infinity, it will go to negative 1. So because of that, y equal to 1 is a horizontal asymptote. And we can say y equal to that number is a horizontal asymptote also. Right. Later on we'll get back to this problem and we'll do that by hand. But for now, I just look at the graph, and that's all we do here for now. Right. Now find the limit of this function. Right. So how do we do this? Right. So when we find the limit, firstly, because we put in numbers, we cannot really put infinity into it, right? Because infinity is not really a number. So let's look at that in a sense of, let's say we're going to have, let's say x go to negative infinity, right? So how about a very small number, like negative 100, let's say that, stored to x. And what happens if we have 2 plus 10 divided by x squared? Right, 2.001. Now, it go to negative infinity, right? So it is a lot smaller. By smaller, I mean on the negative side. So let's try that instead. And that's go by this. So how about a little more? The calculator even cannot take care of all those error and it round to 2. So yes, the limit is equal to 2. Right. So here what we see, we can rewrite this as, remember, one of the properties of the limit of a sum is the sum of limit. Right. So limit when x go to negative infinity, there's no x here, so that's just equal to 2. And that go to 0 because we have a small number on the top. I mean, I should say a finite number on the top. The bottom will just get bigger and bigger. So look like there's thing to consider here. If we have a finite number on the top and at the bottom it goes to negative infinity or positive infinity, it doesn't matter. If we have finite divided by plus or minus infinity, think about that. We have a finite amount. Divide by 10 people, you have something, right? Divide by 100 people, we have less. Divide by 1,000, even less. The more we divide by, the less we have. Essentially, when the denominator goes to infinity, it goes to 0. So in that case, this goes to 0. So we have 2 plus something that goes to 0. So that's just 0. 2 plus 0 is 2, sorry. So it's got 2. Right? So what thing we get from here is that should come in handy. Right, next. Once again, limit of a sum is the sum of the limits. There's no x here to substitute in, so that's just 5. So what do we have here? A little more difficult, right? Because sine x is not constant. It's not constant. However, what we have is sine x, even though it's not constant, it is bounded. The sine on cosine, the amplitude is 1, meaning that sine, the graph of sine is bounded by negative 1 and 1. Sorry, to be here. Sorry, sine x will look like this. It's between y equal to 1 and y equal to negative 1. So that is y equal to sine x. So sine is between negative 1 and 1. Right? Now we divide by square root of x on both sides. And since x goes to infinity, it is positive. And divide by positive, we don't switch inequality. Inequality will stay. Now, as x goes to infinity, we have a finite number, positive or negative, doesn't matter, because it ends up being 0, positive or negative, still. Doesn't matter. So in this case, we have this one goes to 0, this one goes to 0, so the middle have to be 0 as well. And what we use there is called the squeeze theorem. Right? We did use this back in section 2.3. So that go to 0, so we just have 5 here. Right? So essentially that's all we do. What we take out from this is if we have a finite amount, the more we divide by, the less we have. And essentially we just write this. So what new in this section will be this, the note. If we have a finite number divided by infinity, I just say plus or minus infinity, doesn't matter, plus or minus, it is equal to 0. And then next, if we flip that, if we have plus or minus infinity divided by finite. Now this is easy. If you have infinity divided by 2, what do we have? Still infinity, right? So infinity divided by 2 is still infinity. However, when we write like this, potentially that finite number could be positive, could be negative. So to be sure, it's going to be plus or minus infinity. The sign depends on whether we have positive or negative divided by each other. And then the things that left, of course, finite divided by finite, obviously it's finite. Unless we divide by 0, different story. But here, what happened if we have, one more case. What if we have plus or minus infinity divided by plus or minus infinity? In this case, we call that indeterminate. So in section 2.3, we wrote something like this, and 2.4, we wrote that again, and let me show you. So this is in 2.4. We have this, where we have 0. 0 divided by something else is 0. 0 divided by 0 is indeterminate. And 0 divided by something else divided by 0 is undefined. But we consider one of those two cases. Now those will be 0. Now we have infinity. So 0 divided by 0, infinity divided by infinity, both of them are indeterminate. 0 divided by anything else is 0. Infinity divided by anything else is infinity. It could be plus, could be minus. And then the other cases. So those two are very important when we find the limits of a function, especially rational function. Right. Now, after that we have a bunch of definition and theorem. This is nice and all, but it says that if the function is arbitrarily large, so it says that when x goes to infinity, the function could essentially go to infinity. Of course, it could go to negative infinity when x goes to negative infinity. So there's different scenario. X could go to positive or negative infinity. The function could go to positive or negative infinity. So we have 4 different scenarios here, and it's defined similarly. Next, we have a bunch of theorems here. Nice and all, but we don't really need all of that. Right. So it says that let n be positive integers, and then we have like that. It's a lot more than we need to worry about. Right, that's too much. What you need to know in this section is that, which is good. And then instead of trying to understand every single one of the theorem, I'm just going to summarize this. For polynomials, now this is very important. For polynomial, only the leading coefficient, or I should say only the highest power, So that is what I get from doing on the theorem. It's not exactly the same, but you see, enough for us to do pretty much all the problem in this section. Couple that with what we have here. Alright, so let's take a look at these examples. Right, when x goes to negative infinity, I forgot one important thing. For polynomial, only highest power term matters. This is very important here. As x goes to infinity, right? That is, yeah. Without this, it doesn't make any sense. So, as x goes to negative or positive infinity, only the highest power term matters. Right? We have to have x go to infinity or negative infinity. Right, now, since x goes to negative infinity, we have to have that. Then only the highest power term matters. So this we have equal to limit as x goes to negative infinity up to x to the 4th power. Now we put in negative infinity, see what happens. Negative infinity in for x. Now infinity to the power is still infinity, right? Negative to the 4th power is positive. So this is 2. Negative to infinity is still negative infinity to the 4th power is positive infinity. And times 2 is still infinity. So, yeah. So that's what we do. Right? As x goes to negative infinity or positive infinity, only the one with the highest power matters. And by the way, if you read the textbook, they will do that differently. But I think, like I said, this will be enough for problem. Easier way to do it than what the books show you. Right, to put negative infinity here. And that negative cube is going to be negative. Positive times negative is negative. Right. That's easy enough. Right. How about we do something like this? The next one, again, it goes to negative infinity, right? And we say for polynomials, only the one with the highest power matters, right? But this one we have a rational function. So we'll take the one with the highest power on the top. And x squared, the highest power at the bottom. The term with the highest power on the top. The term with the highest power at the bottom. Cancel one of the x. We have 3 over x. Right? Now let's put the numbers in. 3 divided by negative infinity. What is that? Previous page. Finite divided by infinity is 0. So this one equal to 0. Because finite, which is 3 is the finite number. Divide plus or minus infinity is going to be 0. So that's why this equal to 0. So simple enough, right? This is not the way the book does it. The way the book does it is a little more complicated. What it does, it starts with the problem, right? What it does, it say divide top and bottom by the highest power at the bottom. So the highest power at the bottom is x squared, so I'll divide everything by x squared. x squared over x squared is 1. Here we have 3 over x, 2 over x squared. And then we're using the same thing, finite divided by infinity is 0. So x go to negative infinity, so that one go to 0, that one go to 0, that one go to 0. And essentially we have 0 plus 0 over 1 plus 0, 1 minus 0, sorry. Which is 0 divided by 1 is 0. So that's how the book does it. I'm just going to use this fact. I think that works just as good, if not better. Right. The reason the book did not do like this, because actually we have, the way where I do this, we use one theorem that is defined in the, I think, chapter 3. So we put the cart in front of the horse. But that method is valid, certainly valid. Right. What happens when x go to positive or negative infinity here? So highest power on the top, highest power on the bottom. The x cubed cancel out. And then we have 2 over 5, 2 over negative 5, or we have 2 negative 2/5. And because there's no x to substitute in, so that is our limit. Right? So that's why x go to infinity or negative infinity, it does not matter here. Right? This. Right. Usually if we have some other numbers, I'm going to substitute in and see what happened. But on this one, because it go to negative or positive infinity, I will take the highest power on the top, the highest power on the bottom, and just go from there. To x cubed. And then x plus 1. Just x, right? Simplify the x. X cubed divided by x, so that gives us 2x squared. And now when we put in negative infinity, a negative square is positive. So that gives us infinity. Right, now the next one is a bit more interesting because we don't have polynomial, we have a little more than that. Sine x, and then x to the fourth minus x, absolute values of x. Right. So, x still go to infinity though. Now I'm have to write a little thing here. Sine x, we mentioned about that between negative 1 and 1, right? Since sine x is between negative 1 and 1, and x go to infinity, infinity plus 1 or minus 1, actually it doesn't matter, right? If x go to infinity, the x squared and the minus 3x is a lot bigger than the negative 1 and 1. So sine x is negligible compared to x squared and 3x. Negligibly small. I'm not sure if it is a word or not, but it is too small compared to x squared. So in that case, we just take the highest power and x squared will be sufficient. And also, even though absolute values is not really polynomial, but absolute values of infinity is still infinity, but x to the fourth has a higher power. So in this case, we just take the highest power on the top, the highest power on the bottom. Still work. The sine x is too small compared to it. The absolute value of x is too small compared to x to the fourth power. So we still can do this. X squared and x to the fourth cancel out. That gives us 1 over x squared. And here we have 1 over infinity square, or 1 over infinity. Finite divided by infinity is equal to 0. So that's why this is equal to 0. Right. So this extends further than just polynomial. We might have sine, cosine, or even we might have something bizarre like this. We might have even something like even that. Square root of x is equivalent to x to the 1/2. So the power 1/2 is less than 3 and the 2/3 is less than 2. So we still take the highest power here. Again, x to the 1/2 is equivalent to square root of x. So that's why this has a higher power. So it doesn't have to be polynomial. The power doesn't have to be integers. It could be any power, any number. And only the higher power matters as x goes to infinity. Right? And you'll say, what happens if we have like x to the -1 power? Well, right? What happens if we have that? X to -1 power is like 1 over x. It is equal to 1 over x. If x goes to infinity, that one goes to 0. So once again, this one still a lot bigger than that. So still work, the power still work if it is negative. Still the one with the higher power matters. As x goes to infinity or negative infinity, the one with the higher power matters. Doesn't matter if the power is the whole number, a negative number, still higher power matters. Right. How about this one? Yeah. So we start the same way. I'll take the highest power. Except this one, there's the square root. And what do we do with that? Right. Get back to this later. Now what we do is that, let's go back to the beginning of this section. Remember, that's page 13 by the way. We did say that we get back to this problem and we do that manually by hand, right? Now let's do this first and then we go back to our problem. Right, so yeah, there's a note. So what do we write in the note? So since this we do two different ways, I mean two different problems, one go to infinity, one to negative infinity. So we do fold the page in half. Right, first problem. By the way, forgot to mention, this is the way I write number 1 in Roman numeral, the lowercase Roman numeral, because we have 1 and then A, so 1, 2, 3 in subsection, subtitle is A, B, C, and then after that I want to write 1, 2, 3, but I don't want to use 1, 2, 3, so I use the lowercase Roman numeral. So that is 1, that is 2. right, limit of this function right. Once again, the one with the higher power matters. That only at x, when x go to infinity though. If x go to something else, don't ever do this. And we have that. And then you say, doesn't that cancel out? In this case, I say yes. But in general, no. So that's why we have a note here. That note is when we have the square root of something square, it is not cancelled out. Square root does not cancel the square. It gives us absolute values of that number though. Think about this. Square root of negative 3 square. That does not cancel, right? The answer is not negative 3. That would be wrong. Because negative 3 square is 9, square root of 9 is positive 3. So the answer is always positive. So that's why we throw in the absolute values. So once again, square root does not cancel the square. Give us absolute values instead. And absolute values meaning that it is positive. It is itself if it is greater than or equal to 0. And opposite to that if it's less than 0. Right. So in this case, x go to infinity, meaning that x greater than 0, right? So since x greater than 0, square root of x squared is equal to absolute value of x, and x is greater than 0, absolute value is itself. So if we can we just have limit x go to infinity of x, square of x square is equal to x in this case, and that is limit of 1. There's no x to substitute in, so that is equal to 1. So that's why we have the graph confirmed it equal to 1. Right. 2. What happened when x go to negative infinity? Same function. Now, once again, I will take the highest power on the top and the highest power at the bottom because x go to negative infinity. Yeah. Go to negative infinity, take the highest power on the top, highest power at the bottom. Now, when x go to negative infinity, it is negative, right? Yeah, to go to this side, suddenly negative. So since x is negative, square root of x squared is absolute value of x. Absolute value of a negative number is going to be opposite to that, right? Because x is negative, negative, negative is positive. So I'm not saying about the negative, I'm not saying this is negative, I'm just saying that is opposite instead of negative, right? Regardless, we have x on the top, at the bottom, square root of x squared is negative. Sorry, I say that again. Square root of x squared when x less than 0 is opposite to x. X and x cancel out, it's negative 1. And there's no x to substitute in, so it's still negative 1. Right. So be mindful when we have the square root of the square. They do not cancel. It is equal to absolute values instead. And that's what we have. Right, now get back to our problem. Here we have this. So, what's that? Is that going to be x squared or negative x squared? So, let's just rewrite like this. X to the fourth can be written as x squared square. So let's just write out again the formula. So here we have square root of x squared square is absolute values of x squared. Now, the difference here is even though x go to negative infinity, x squared is still positive, right? X squared is always greater than or equal to 0. So, as x go to negative infinity, x squared go to infinity, right? Negative infinity square is infinity, meaning it's positive. So if it is positive, it will equal to just itself because it's positive. So even though it go to negative infinity, right? But this one, we don't have the negative. So be mindful about that. So that's why I make this to an even power. Right. So that is equal to just x squared now. X squared for x squared is 1. So this is just 1. So simple enough. Right. So be careful with that. And I'm writing a instead of x because x could go to negative or positive infinity. What we worry about is the actual expression here. We have x squared and not x. So that's why even though x go to negative infinity, x squared still go to infinity. Right. Next we have the slant asymptote or the oblique asymptote. So when the function approaches a linear function f x, then the line L is called the slant asymptote. Right. I just put that completion, that definition there to complete the section, although we don't worry about much of the slant asymptote here. So I just want to draw a graph instead. So the slant asymptote might look like a line that is not horizontal or vertical, and the function might be, I just also add a vertical line to it, so the function might be look like this. It approaching to that line. Yeah. So the slant asymptote is a slant line. Right. So let's do a few more examples. Examine the end behavior of sine, cosine. Right. So we talk about this sine function going like this. And cosine all we know is that sine x or cosine of x between -1 and 1. So usually when we have this, we can use the square theorem, but there's no limit. Limit does not exist because the function just go up and down. We don't have exact values for it. So limit as x goes to infinity of sine x does not exist. Could be positive or negative, still does not exist. So in general, it does not exist. But more often than not, we can use this. And I certainly use that to compare when we see this problem, when we do this problem. Yeah. So if I want to, in this problem, I can add, let's say, sine x into it, and the problem is still the same, because the sine x is significantly smaller than x cubed. So x cubed is still the higher power than sine of x. So I can add sine x there, and the problem is still the same. Right. Next, I'll find the vertical asymptotes and horizontal asymptote of this one. Right. So I ask you which one is easier to find, horizontal asymptote or vertical asymptote. For this problem, it will be very easy on both of them. But in general, it is easier to find the horizontal asymptote because we just take the limit go to infinity. Right? So horizontal asymptote is y equal to the limit as x goes to infinity or x go to negative infinity. And then you ask, do we have to do both? And the answer is yes, we have to do both. On this one doesn't matter, but the next one it will. Right, so all I need to do is just find the limit of 10x over 2x minus 3. Right, so x go to infinity, meaning that highest power matter. X and x cancel out. 2 over 10 over 2 is 5. So we just have 5, which is 5. Now, same thing. But this time go to negative infinity. Still, we can take the highest power, cancel out of x. 10 over 2 is 5. We still have 5. That means when x go to infinity or negative infinity, both of them equal to 5. So y equal to 5 is a horizontal asymptote. It is easier to find the horizontal asymptote. The vertical asymptote, we don't know which one though. So vertical asymptote. So how do we find the vertical asymptote? Right, so that from the previous section. So the vertical asymptote is where the function approaching to infinity where x go to a constant. The problem is we don't know what is that constant. But vertical asymptote happen when we have something other than 0 divided by 0. Right, so vertical asymptote is where we have, I just want to say it, when we have 0 divided by something other than 0. Yeah. I'm sorry, I brought that backward, did I? because 0 divided by anything else is going to be 0. Sorry, I brought them backward. Yeah. So watch out for the case where we have something else than 0 divided by 0. Should not write the plus or minus because that looks like a different sign. So not equal to 0 divided by 0, meaning that the bottom is 0 and the top is not. If both of them equal to 0, we have a hole instead of the vertical asymptote. So in this case, the bottom equal to 0, to x minus 3 equal to 0. In this case, vertical asymptote is relatively easy to find. So x equal to 3/2. And then we need to make sure that the top is not equal to 0. As x equal to 3/2, the top equal to 10 times 3/2, and that's not equal to 0 because that equal to 30. I'm sorry, I mean 15. So yes, top not equal to 0, bottom equal to 0. So x equal to 3/2 is a vertical asymptote. So when we have the vertical asymptote, we consider the case here because potentially that goes to infinity or negative infinity. But that's exactly what we did in course algebra, although we did not explain why do we do this. Now we have the limits. It's easier to explain. Right, horizontal asymptote, vertical asymptote, same thing. Let's find the limits. As x goes to infinity of that. Sorry, there's a typo here. Please change this to a plus. Or should we? Never mind. Mine is still fine. Yeah. Never mind. Sorry about that. A lot more interesting though. Right. In this problem, it doesn't matter. Right. X go to infinity. Only the highest power matters. Now square root of x squared is absolute values of x. Since x goes to infinity, x positive. So absolute value of x when x positive is itself. By the way, we can also just put on the graph square root of x squared. It is exactly the same as absolute values. Absolute values is alpha Windows. If that works, if you don't want to do that, I'm sorry, if you don't want to do that, hit math and all the way down to, where was that? Oh, second tab, numerical. Absolute values. Yeah, you see the graph are the same, right? But then you say if it's the same, then how do we see it? Of course we don't, like this. So if you want to see the graph actually the same, go back all the way to the left. By the way, this is not related to the section, but it's interesting nevertheless. Just move all the way to the left, hit enter until you see that icon. Now you see that is square root of x squared, and then it graph the second one, so it traces the second graph. Over the first graph, so they are the same. Yeah, so we can move to the left to change the pattern of the graph. Here we can draw the double line. Yeah, so that's what we can. Yeah, we did have the standard window, so right, that's fine. Right, so that equal to x. So we will have limit x go to infinity of 2x over x. X cancel out, so that is 2. Next, find the limit when x go to negative infinity. Still the same thing though. Highest power terms matter because x go to negative infinity. But this time we have negative of x squared. X squared, square root of x squared, absolute value of x. Since x go to negative infinity, x is negative. X less than 0. If x is negative, absolute values of x is going to be opposite to x. So in this case, we have just 2x divided by negative x. To x over opposite to x. X and x cancel out, that is negative 2. So we have y equal to 2 and y equal to negative 2 asymptotes. And then answer the question that you may ask earlier, do we have to find the limit from both negative and positive and negative infinity? And the answer is yes, because they might be different. So y equal to 2 and y equal to negative 2 are the asymptotes. Horizontal asymptote. Right, so that is horizontal asymptote. And then the vertical asymptotes. Vertical asymptote similar to what we have earlier. The bottom has to go to 0, the top something else. Right, so we have the bottom equal to 0. I can square both sides. And we have x equal to 1 or x equal to negative 1. Take the square root both sides. Let's be careful with this. This example is perfect example to go to the next section. So take the square root on both sides. Make sure there's a plus or minus. So that would be x equal to plus or minus 1. and then at x equal to 1 or negative 1, the top is not equal to 0. So x equal to 1 or negative 1 are the vertical asymptotes. However, there's a lot different than this on this one than the others problem. Let's look at the graph. I put an asterisk here because it's slightly different. So we have that, right? So obviously there is the vertical asymptote at negative 1 and 1, which is what we have. Horizontal asymptote at 2 and negative 2. That's what we have, which is good. So what we did here is nothing wrong. What I want to emphasize is that the function is undefined from negative 1 to 1. So that asterisk, that's what I want to bring up. For x between negative 1 and 1, the function is undefined. Because if we have x equal to 1, the bottom is 0, divided by 0 is undefined, that's for sure. If x is less than negative 1 and 1, we have something less than 1, subtract 1, meaning we have a negative inside square root. Square root of a negative number is imaginary, and imaginary is not real, meaning it's not defined in the real numbers. So that's why it's undefined, because square root of a negative is imaginary. If we have a number less than negative, between negative 1 and 1, like 0.5, 0.5 square, 0.25 minus 1, that's negative. Square root of a negative number is undefined in real numbers. It is imaginary, but still. So in this case, we have to be mindful to that. So if we write the limit for this scenarios, I will say it from negative 1 and 1 is undefined here. So I can only say it, limit when x go to negative 1 on the left, which is still okay though, right? So if we go from the left of negative 1, it's still okay. But if I write the limit of x go to negative 1 from the right, for sure it's going to be undefined, or does not exist, because the function is undefined from negative 1 to 1, right? So there's no limit. If the functions, remember the definition of limit, suppose the function is defined near a, and this one is not defined near 1, near negative 1. So this limit does not exist because the function does not define at all in that interval. It defined on the left side though, so we still have limit from the left, but we don't have the limit between negative 1 and 1 because the function does not define in that interval. Right. So bottom line, the way we define the limit is that where the function has to be defined near the point where x approaching to. If it does not define, there's no limit. Right. So with that, stop section 2.5 here. As always, thank you for watching.